Crazy, busy and very deadly times. But be that as it may, welcome to yet another Mathologer video. Today I revisit a topic that I touched upon a couple of years ago. Today we look at a mathematical leap of faith performed by the 18th century mathematician, the amazing Leonhard Euler. There, it's Euler again. Euler's crazy leap of faith resulted in a magic key that opens the way to the most famous and most beautiful formulas for pi. In particular, what I'd like to do today is to again quickly perform that leap of faith together with you, and then show you some breathtaking animated algebra that will get us once more the Leibniz-Madhava formula for pi, and John Wallis' infinite product formula, and William Brounker's spectacular infinite fraction formula, and Leonhard Euler's amazing formula solving the Basel problem, which made the 28-year-old Euler a mathematical superstar. Plenty of magic for today, right? But wait, there's more. I'll also show you how the infinitely many higher power counterparts of the Basel formula can be obtained. That one there, and that one, and on as far as you want to go. One Basel type identity for each even power of pi. Amazing stuff, huh? Really, really, really amazing stuff. This video was inspired by a one-page article by Paul Leverrier in the Mathematical Intelligencer in 2012. In this article, Leverrier sketches some lightning-quick derivations of some of these results. They really are a must animate, I think. Anyway, I'll put a link in the description. Okay, here's a question for you. Let's say I tell you that my pet cubic has zeros at -1, 0 and 1. Is this information enough to pin down my cubic? What do you think? Well, the answer is almost. Here's one cubic that has these 3 zeros. So the cubic is a product with one factor for each zero. Then you can get all the other possible cubics with those zeros by stretching in the vertical direction, by scaling with non-zero constants. Easy stuff, right? And most of you will know that the same is true for polynomials in general. If you know the n zeros of an nth degree polynomial, then you can capture your polynomial as a product, except for scaling. Now, Euler and his buddies were experts at thinking of functions such as the exponential function and the trig functions as infinite polynomials. There, that's the famous Maclaurin series for the sine function, one of these infinite polynomials. Now, Euler wondered whether because functions like sine had representations as infinite polynomials, they could also be written as products based on their zeros. And, as crazy as this idea may sound at first, Euler managed to get this to work for sine. Here's what he did. Okay, are you ready for some seriously mad flight of mathematical fantasy? Sure? All right then, madly we go forth. Let's ignore the Maclaurin series and hunt again for the polynomial for sine of x, just as we did for the cubic. So, begin with the zeros. Sine has infinitely many of them. And so our mad formula for sine should be an infinite product with one factor for each zero. Let's assemble them into a product from the inside out like this. Then, if all goes well, sine should somehow be this product times some non-zero constant. It looks pretty insane, right? But let's just tell our brains to shut up and let's keep following Euler on his flight of imagination. To determine the constant, Euler just goes for it and divides by x. The new function on the left looks like this, peters out, right, like that. Okay, let's evaluate everything inside at 0. There we go. Okay, there. On the right we've got, oh well, whatever that is, it should be infinity. And on the left we're dividing by 0. Double. Okay, left side. Sine x divided by x is definitely not defined at 0. However, although sine x divided by x is not defined at 0, its limit at 0 is 1. Close our eyes, close our brains and keep going. Divide by c, flip both sides. Voila, that's our c. Whatever the hell it means. But don't worry, mad and brainless we go on. It ends soon, I promise. Let's plug this crazy c into our original formula. We'll do it carefully, so the pi denominators and the 2 pi denominators and so forth line up with the other factors. Yeah, like that. Now a little cancelling. There, and there, and there, and there, and there. Now, of course, the reasoning that led us here is completely crazy. But believe it or not, this final formula really makes sense and really is true. I haven't given you anything like a proof of the formula, but I can give you a sense of how the formula works. To sneak up on that infinite product, let's start multiplying out those factors and let's plot the partial products along the way. Then those partial products get closer and closer to the sine function. So the first partial product is just x. Again, it's very important to realize that the crazy flight of fantasy that led to this formula is very, 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 very far away from a proof. But it is also important to realize that mathematicians don't just work by trying to prove things. The Nike method, just do it and see what happens, can result in great insights. And the Nike method, in the hands of a genius like Euler, can result in miracles. Of course, any discovery made the Nike way still has to be confirmed by a rigorous proof. There is no way around that in mathematics. Anyway, first mission accomplished. We have Euler's amazing product formula to play with. Our second mission today is to push and pull and prod Euler's formula to derive pretty much all the most famous infinite expressions for pi. Okay, we're talking infinite sum, product and fraction identities for pi. What do you think is easiest to do? Well, the right side of Euler's identity is a product, and so a product should be easiest, right? And it is. Alright, so let's chase down that product formula for pi. Actually, really straightforward. The most obvious thing to try is plugging in pi for x, but that doesn't work. We just get 0 for sine x and also on the other side 0. So 0 is equal to 0. No, not good. But the next most obvious thing to try works. Plug in pi over 2 for x and see what happens. Fantastic! Wallis's product formula is really just Euler's product evaluated at pi over 2. Pretty sure that Wallis would have enjoyed this. What's next? What sounds easier to do, an infinite sum or an infinite continued fraction? The infinite sum, right? Okay, we are after a sum. And how do you turn a product into a sum? You know the answer to that, or at least once upon a time in school you did. Logarithms, remember now? Log of a times b is equal to log a plus log b. Well, we'll do exactly the same thing, just with a slightly bigger product. And we'll use the natural logarithm. Well, that's great. Our product is now a sum and we can think about plugging in or whatnot. But what about those logs? How do we get rid of them? Well, that's easy. You simply differentiate. Here we go. And now we can plug in. What value should we choose for x? Well, 0 and pi actually explode the right side, so they definitely won't work. What about pi over 2? Oh, have a look. That makes the left side 0, which feels like it might be good, but we also end up with the right terms cancelling in pairs. So no dice. Probably the next most obvious value is to try is x is equal to pi over 4. And yep, that works. Here we go. Ta-da! So you get the Leibniz-Madhava formula from Euler's product formula by simply applying a logarithm, differentiating and evaluating at pi over 4. Simply magic. Next, I'd like to show you an ingenious way to derive this amazing infinite fraction from our Leibniz-Madhava infinite sum formula. That one there. So let's first recast this infinite fraction formula in terms of the infinite sum in the Leibniz-Madhava formula. First off, that 1 right at the beginning of the infinite fraction is a bit of an oddball, right? Since there are 2's everywhere else. We could add on both sides of the equation to get all 2's, but after some experimenting, it turns out to be better to subtract the 1 from both sides, like that. Now the Leibniz-Madhava formula features pi over 4 and not 4 over pi. That's easily fixed. Like that. Now make the left side into one big fraction like that. Okay, not so simple, but at least it's pi over 4-ish. That means we can now plug in our infinite sum for pi over 4. So what we want to show is that that scary fraction on the left can be magically manipulated into the infinite fraction on the right. Ready? Not too scared? Well, then let's do it. Okay, a good easy step to begin with. Let's get rid of the brackets. Now, I'm going to show you a clever mathematical combo move. We'll be repeating this combo move over and over, so pay careful attention. The combo move begins by manipulating the denominator. 2/3. We want to end up with 1's in all the numerators, just as we started. So to get there, as the next part of the combo move, we employ a sneaky trick, adding and subtracting a clever expression. Right? The pink and the green cancel, so we haven't changed the denominator. But how does this do nothing step help? Well, let's see. Our do nothing step arranged for us to have the same pink number at the top and at the bottom. And our final step in the combo is to divide through by that pink number. And that almost finishes our first magic combo movement. Remember, we started with this fraction of infinite sums. Now, just focusing on the green and pink fractions, the new one on the right results from the one we started with on the left by discarding the leading terms and multiplying through with -1. And as I said, what we'll do is to repeat this magical combo move over and over, which will make the green and pink fraction disappear. What comes out is this beautiful infinite fraction. But we're not quite ready. We need one more mini step to control things down to infinity. Spot the difference? Not hard. On the left we've got a 3, and in the final fraction we're after, we've got a 3 squared. To get the square happening, our last mini step is very similar to our add and subtract trick. Here we multiply and divide by the same number. Have a look. Neat, huh? That's the end result of our magical combo move. And now we just started up again. Just watch and wonder. Brilliant. But what does this actually show again? Well, remember the oddball 1 that we moved to the left? What we've shown is this. And kicking the oddball 1 back to the right, we get Brounker's fantastic fraction. But there's more. Let's do reciprocals on both sides. 1 over both sides. Of course, that means the infinite fraction and the infinite sum are equal, right? But not only that. On close inspection, it turns out that even all corresponding partial fractions and sums are equal. There, the first partial fraction and the first partial sum are both equal to 1. The second partial fraction and sum are both equal to 2/3, and so on. Amazing, right? And just in case you were wondering whether this is obvious, nope, but it's also not too difficult to prove. So we have our infinite fraction. What's next? Our final goals are Euler's Basel formula and its infinitely many cousins. These were really what Euler was after when he conjured up his product formula for sine. The idea here is to expand the infinite product and collect together the different powers of x. Now, before the monster expansion, we first do an easy simplification of the product. Notice that each successive pair is a difference of 2 squares. So we can simplify like this. Okay. Enough dilly-dallying. Time to expand. To do this, we take one term from each factor and multiply them. And we do that in all possible ways. Let's go. First, let's take the x from the first factor, no choice there, right? And choose the 1 in all other factors. Multiplying the x and all those ones together gives us, yep, you guessed it, x. Next, what if we change our choice in the first bracket to minus x squared divided by pi squared, but keep all the other ones? Well, then the resulting product is x times that x squared term, which results in minus x cubed divided by pi squared. Got the idea? Great. Each sequence of choices gives us one term of our final sum. So let's think about the terms that we'll get out, starting with the lowest powers. Obviously, this expansion only contains the one x term we've already obtained, that one there. What about x squared terms? Nope, no way we can get those. And the same for any even powers of x. On to the x cubed. Well, there's the one we've already found. And here's another one. And another one. And so on. This means that the expansion of Euler's product starts out like this. Can you see what's coming? Taylor series fans can take a shortcut here, but let's take the slow and easy road. To make the x cubed disappear, we'll differentiate. So differentiate once, differentiate again, and one last time. Done. Now set x equal to 0. That wipes out everything on the right except for the first constant term. And of course, cos of 0 on the left is 1. Time to relax and go into easy autopilot. And there you have it. Euler's celebrated Basel formula. And that's how Euler originally derived it. Simply magnificent, isn't it? But why stop there? In for a penny, in for infinitely many pounds. Euler also noticed that we can get a whole lot more if we just keep going. Okay, so where were we? We differentiated twice, and at this stage we plugged in x is equal to 0. But instead of plugging in, let's differentiate 2 more times. That gets rid of the x squared we see here. Can you see it? Well, differentiate once and one more time. Now we're ready. Plug in x is equal to 0 as we did before. Impressed? No? Don't worry, you soon will be. So what's the mystery stuff in the bracket? Well, these are all the coefficients of the x to the power of 5 terms in the original expansion. So let's go back to remind ourselves what happened there. To get the x cubed terms, we picked the x in front and one of the x squared terms, and all the rest once. So how do we get x to the power of 5 terms? Easy, right? We pick the x in front and 2 x squared terms, and then all the rest once, like this, or like this, or like this. In general, these x to the power of 5 products look like this, with I being less than j. And so the bit in the brackets we are after is just the sum of all these coefficients there, those ones. And switching to algebra autopilot, we get this. That's great, but that's not the sum we're after. We get the sum we're after if we replace the less than sign by an equal sign, like this. There, that's what we're really after, the sum of the reciprocals of the 4th powers of the integers. Okay, but how does the green less than sum help with that? Well, the thing is, we already know something else, namely this sum there. That third sum ranges over all possible pairs I and j without any restrictions. But how do we know that sum? Can you see it? That third sum is just the square of the Euler-Basel sum. Got it now? That means the third sum is the square of pi squared over 6. Can you see where I'm heading with all this? If not, don't worry, from here it's easy peasy. Apart from the blue equal sum and the green less than sum, there's also a red greater than sum. Yet another sum, but this one we know right off. Because of the symmetry, just swapping I and j, the red greater than sum equals the green less than sum. And now everything's falling into place, right? Of course, the blue plus the green plus the red is equal to the orange. And now just plug in all the values of the sums we know and we get this. And from this we get the value of the blue sum that we've been chasing. Very, very pretty also, don't you think? And we can play the whole game once again. If you differentiate our expanded product formula twice more and manipulate the result in the same way we just did here, we get Euler's pi to the power of 6 formula. Keep going, we get the pi to the power of 8 formula and so on. This gets more and more involved, but in principle, the type of manipulation needed to be done is always the same. Come to think of it, I have not assigned any homework yet today. Terrible, isn't it? So for those of you desperate for some challenges, why don't you try to derive the pi to the power of 6 formula up there? Also, apart from all the craziness in the Nike derivation of the product formula for sine, there are quite a few details that are glossed over in the derivation of the pi formulas that really need to be nutted out to make these derivations into rigorous proofs. So here's another challenge then. What are those details? How many can you spot? For example, wasn't there a detail in the expansion of Euler's product for sine that needed some extra attention? Anyway, returning to these Basel formulas, Euler also managed to find a general superformula that encapsulates all these infinite sums. Most of you methodologists would have seen this superformula previously. It's connected to the famous Riemann-Zeta function and popped up in my video about the Bernoulli numbers and the Euler-Maclaurin formula. Check it out. Oh, and one last note. For the experts among you, Euler's infinite product formula for sine is just one incarnation of the so-called Weierstrass factorization theorem. This theorem says that every so-called entire function can be represented as a product involving its zeros. And that's it for today. I trust you enjoyed this wonderful mathematical journey. See you next time, hopefully with the world in a safer and happier place.